A star group or cluster is when stars of common origin are held together by gravitational attraction. They can be main sequence stars, red giants, white dwarfs, neutron stars, binary stars, or black holes. Stars are not fixed and are unchanging. They are formed, evolved, and eventually use up all their energy sources to end up as some type of stellar residue. Stars are not alive, yet they follow a life cycle and go through stellar evolution. All stars require an energy source to keep them from collapsing. Forces of gravity and radiation pressure released from the star balance each other out and resist collapse. 90% of the stars in the universe are main sequence stars, including the Sun. Their masses can range up to 1/10 of the Sun to up to 200 times as big. Main sequence stars fuse hydrogen atoms to form helium atoms in their nuclei. During this process, small amounts of mass is converted into energy released from gamma photons. Hydrogen fusion is mostly made up of proton-proton chains. In the end, 4 protons are fused to form a helium-4 nucleus, gamma photons, positrons, and neutrons. Radiation pressure created by this hydrogen fusion helps the main sequence stars from collapsing under gravity. The product mass is less than the combined reactants as the difference is converted into energy. Their energy source is the CNO cycle, which is the fusion of carbon, nitrogen, and oxygen. This was founded by Hans Bethe and Carl von Weizsäcker. The result is the same as a proton-proton chain. The greater the mass of the main sequence star, the higher its temperature and the greater its rate of hydrogen fusion. Therefore, stars with higher mass produce more energy, and so they have a higher light intensity. Higher mass stars consume their hydrogen faster than lower mass stars. Our Sun has enough hydrogen to last 10 billion years, whereas an extremely massive star may only survive 3 or 4 billion years. When a main sequence star uses up all of its hydrogen, the fusion will stop and it will no longer emit radiation pressure. This now becomes a red giant. In 5 billion years, our Sun will run out of its fuel and it will begin to expand 100 times, and it will destroy Mercury and Venus. However, Earth will be spared because as the Sun expands, so will its gravitational field. The red giant then undergoes the triple alpha process, with 3 helium atoms fused with 1 carbon atom. This causes the star to grow bigger. The helium atom in the nucleus begins to contract, turning the gravitational potential energy into heat energy. This rise in temperature heats up the hydrogen surrounding the shell until it is hot enough to continue hydrogen fusion. This produces more heat than the main sequence star. The increased radiation pressure causes the star's burning shell to expand, and as the gas expands it cools down, and as the temperature drops the star appears redder. A white dwarf, or a degenerate dwarf, has no radiation pressure to resist gravitational collapse. It is the pressure produced by the surrounding electrons that stop the star from disintegrating. Fusion in the core stops once all the helium has been converted into carbon. A white dwarf can reach up to 100,000 Kelvin once it has stopped contracting. White dwarfs are extremely bright because they have trapped heat from the earlier stages of evolution. Because there is no radiation being emitted anymore, the star begins to cool, hence why they are white. If a white dwarf is alone, it will cool enough to become invisible. This is called a black dwarf. If a white dwarf is located close to a binary star, hydrogen falls down onto the star. This is hot enough to turn the hydrogen into helium, releasing energy called nova. If too much energy is generated, a supernova is created. A binary star is a system of two stars that revolve around each other or a common center. Binary stars obey Kepler's laws of planetary motion, and from this and through the aid of vectors, astronomers are able to determine the mass of stars. When two stars are close enough, they transfer matter to each other, and they survive off each other's resources. A neutron star is the result of a gravitational collapse of a supernova. Energy production stops when the core burns into iron. The core suddenly collapses, compressing the electrons and protons to form neutrons. They are the densest and smallest stars, and can easily collide with black holes. A black hole forms when a massive star has no energy left in its core. It is usually the result of a supernova explosion. They compress the mass of a star until it is so dense that gravity collapses into a limitless point. It can swallow anything nearby, including light. Therefore, main sequence stars, red giants, white dwarfs, binary stars, neutron stars, and black holes all have an energy source that helps the star to produce energy and to keep it from collapsing under gravity. It is because of these energy sources and the radiation it emits that some stars are hotter, brighter, or bigger than others. And from using these energy sources of the star groups to determine their properties, astronomers have discovered so much more in the solar system. Thank you for watching, and I hope you enjoyed.